Let us move on to liquid propellant systems. I will go through this part a little bit quickly. Okay. As far as calculating equilibrium states or designing a liquid propulsion system for a given application, assuming that it will not go into instability issues, the choice is very simple. What is shown in this plot is the ISP versus propellant O by F, and the important curves for the purposes of the current discussion are this red curve, which is for N2O4 and monomethyl hydrazine, earth storable propellant combination, also hypergolic, used in small rockets, okay, and in initial stages and upper stages where we want guaranteed ignition. The other important rocket is the cryogenic rocket, which uses liquid oxygen and liquid hydrogen, which has the, as you can see, has the highest specific impulse and therefore is required for long missions. Okay. When you want rocket motors to work for longer duration, the savings in terms of the propellant that needs to be carried when you use a cryogenic rocket motor is significant, and therefore you want to use cryogenic systems for longer missions. What is becoming important recently is the LOX kerosene system, which is shown in cyan color here. This is the LOX kerosene. As you can see, this is a compromise between a full cryogenic system, which is a complex system, and an earth storable system. It gives higher specific impulse than an earth storable system and is being contemplated as a first stage rocket, and another emerging technology is the LOX methane system. As you can see, has a slightly higher specific impulse than the LOX kerosene system, and again being contemplated as a high thrust booster for the first stage. Okay. So the choice is very simple. Small rockets use earth storable propellant with hypergolic ignition. Large rockets requiring a large takeoff thrust should use LOX kerosene, LOX methane systems along with solid strap-on boosters. Long missions should use cryogenic systems. That is all that I want to say about choice of propulsion systems, liquid propulsion systems, and in all these systems the design for equilibrium conditions is the thrust chamber design for equilibrium conditions is always controlled by the droplet size. We saw that the vaporization time goes as d0 squared, and therefore the thrust and this is the rate limiting step, and the thrust chamber should be designed so that complete combustion can be ensured, and that is the only key idea that is required for designing thrust chambers. Of course, I have not discussed anything about the cooling requirements and other things. As far as combustion is concerned, it is only the droplet size that is the key variable, but it is an entirely different question when it comes to the question of stability. Are the equilibrium states stable? Okay. Here again, without going into a lot of details, the key idea seems to be that ensuring that there is a uniform distribution of heat release in the lateral direction leads to stable combustion systems. This can be ensured by making sure that the distribution of the propellants, liquid oxygen and the fuel, is as uniform as it could possibly be made in the lateral direction to avoid coupling with acoustic modes. Classic example of where this was not done and there were serious instability issues was the F1 engine, which used impinging injectors, which inherently creates a very heterogeneous mixture ratio distribution in the lateral direction very close to the injector plate, leading to severe instability issues. On the other hand, The Russian system, the RD-180, which is shown on the right, uses coaxial injectors. This uses impinging injectors, this uses coaxial injectors, which maintains a much more uniform distribution of mixture ratio in the lateral direction. That is one advantage. The other advantage is because the fuel and the oxidizer are not impinging and creating a very intense reaction zone close to the injector plate, since they are flowing coaxially, the heat release zone is distributed in the axial direction and it is also uniform in the lateral direction, preventing coupling with the acoustic modes. Okay. Therefore, the key insight from the analysis of information available in the literature is that what aids stability is distributed reaction zone in the axial direction and uniform distribution of mixture ratio in the lateral direction. Coaxial injectors aid this, impinging injectors do not aid this, and therefore systems using coaxial injectors are much more stable than systems using impinging injectors. This is the only key conclusion that can be drawn from the information available in the literature. The different kinds of injectors are shown here. These are the impinging injectors. Okay, these are the coaxial injectors. Several variants of this was used in the F1 engine, which was used in the moon mission. These are used in the Russian designs. You may ask, then how did the F1 engine work under stable conditions in the moon mission? By the use of baffles. Baffles are necessary to ensure stability in F1 engine. Russian engines also have baffles, but it looks like they are required only to maintain stability during transient operations like startup and throttling, not during steady equilibrium or steady design condition operations. Okay. With that, I will move on to air breathing propulsion systems. 4 systems were discussed. Combustion chambers, gas turbine combustion chambers for civilian applications. Military, Ramjet and a scramjet. Right here you can see the difference between a military gas turbine and a civilian aircraft gas turbine. A military gas turbine has an afterburner. Okay. Another difference is that the military gas turbine engines are low bypass ratio turbofan engines or sometimes just turbojet engines. The civilian aircraft engines are high bypass ratio turbofan engines. The other 2 propulsion systems that are shown here are Ramjet, which is used as far as I know only in weapon systems, not for transportation. Scramjets are being conceived as both a weapon system and a transportation system for space travel and 2-stage to orbit vehicles. Okay. The advantage of an air breathing propulsion system as compared to a rocket propulsion system is that the oxidizer, which is the air, need not be carried along, and therefore the specific impulse of these systems are much higher, an order of magnitude higher than rocket propulsion systems. Of course, with the downside that they cannot operate in outer space, but within, as long as you are within the atmosphere where air is available, these systems can be used. This is a cross section of a military gas turbine engine. It's I can't say from the picture whether it is a low bypass turbofan engine or it looks more like a turbojet engine with an afterburner. Okay. It has a low pressure compressor, a high pressure compressor, and then the combustor here. Okay. A high pressure turbine, a low pressure turbine, and an afterburner system. or also called the reheat system. Okay. The primary combustor uses liquid fuel sprayed into the combustion chamber. Here again droplet size, its dispersion within the combustion chamber and air distribution. Okay. Determines what is called the circumferential pattern factor at the exit of the combustor. This is a measure of the circumferential non-uniformity in temperature. And why is this a key thing? Because this has to be within a certain limit for the life of the turbine to be acceptable. Okay. So typical values are something like 0.32. The circumferential pattern factor must be lower than 0.32. Higher the CPF, higher is the non-uniformity, lower the CPF, lower is the non-uniformity. This must be as low as possible, lower than 0.32 for acceptable turbine life. Okay. And the challenge in designing the primary combustion chamber is predominantly in ensuring that the circumferential pattern factor is under acceptable levels. And this is ensured usually by ensuring that that the droplet distribution produced by different injectors which are placed along the annular along the circumference of the combustion chamber produce more or less the same droplet size distribution, and the droplet sizes are sufficiently fine for combustion to go to completion and the temperature is uniform at the exit. So this is the key challenge in designing the primary combustion chamber. As far as afterburner is concerned, okay, again the fuel is injected as a spray in a much simpler form as compared to a primary combustor, but here the problem is one of acoustic instability called screech. This is a high frequency acoustic instability, and here again the principle that lateral non-uniformities must be minimized to avoid coupling seems to be valid. Remember that in liquid propellant rocket instability problem, it appeared like ensuring lateral homogeneous mixture fraction distribution aids stability. Here again avoiding lateral non-uniformities seem to aid stability. The non-uniformity is predominantly created by the swirl of the flow that comes out of the turbine, and in some designs what is used is a anti-swirl vanes to nullify the effect of the swirl, creating more or less uniform stream of hot gases coming out of the turbine, and that seems to ensure stability, and that is the key idea here. Okay. The next is civilian aircraft. In addition to circumferential pattern factor, okay, again here there is a turbine at the downstream of the combustion chamber, and therefore the circumferential pattern factor has to be low, but the design is not so much limited by this as much as the desire to have low emissions. Okay. The ever increasing stringency of the emission norms has led to adoption of lean premixed combustion systems for primary gas turbine engines. What are the advantages? In a conventional gas turbine system, which is essentially a non-premixed flame system, the equivalence ratio inside the combustion chamber is highly heterogeneous. There are zones which are fuel rich, there are zones that are oxidizer rich, and there are zones that are stoichiometric, and these stoichiometric zones are the problematic ones because they have the highest temperature. Remember, equivalence ratio versus temperature looks like this. Phi equals 1 is the highest temperature, and what is the problem with high temperature? Wherever there is high temperature, there is formation of NOx. NOx is a high temperature problem. So how to decrease NOx is to make the mixture homogeneous and lean. Okay. Homogeneous makes sure that the equivalence ratio everywhere is the same, and lean makes sure that the temperature is sufficiently low for NOx to be low. Of course there is a catch, if you go to very lean conditions the carbon monoxide becomes unacceptable, but that is a trade off that has to be accommodated in the design process. So how is this achieved? Unlike the conventional system where more than 70% of the air, okay, maybe I will give a simple sketch of a conventional combustion system. 100% fuel, 30% air comes through the core, the remaining 70% of the air is distributed along the liner. This is the conventional system. The lean, unlike this, in the lean premix system the fuel, excluding the pilot fuel, all the fuel 100% fuel comes from here, and more than 70% of the air also comes along with the fuel. And what is done with that air? As you can see there are several stages of swirlers here. This is the first stage swirler, this is the second stage swirler, this is the third stage swirler and the fourth stage swirler, and fuel is injected right into this strongly swirling air stream, and in this zone a close to premixed mixture is created, and that premixed mixture issues out of the fuel injection air injection system to create a lean premixed flame. You would still require a non-premixed pilot flame at low loads and to ensure stability of the flame, but most of the heat release happens in the lean premix conditions, leading to ultra low NOx. Not that everything is great with this system, there are instability issues that have to be dealt with, and it has been several novel designs have been evolved over the last 20 years. One such design is the GE TAPS 2 combustion chamber and the Pratt & Whitney Talon X. Okay. While the basic idea is to go lean and premixed, this has been achieved using a variety of strategies, and two good examples of two different strategies that have been used for this is what you can see in the GE TAPS 2 engine and the P&W Pratt & Whitney Talon X engine. But the basic idea is to go lean premixed, to go to low temperatures to avoid thermal NOx. Ramjets, I said, are mostly used in weapon systems. Disadvantages are thrust is 0 at Mach number 0, startup thrust is 0, so you need to take it using another vehicle to sufficiently high Mach numbers of about greater than 2 for it to produce useful thrust. Greater than 0 only when you go to large Mach numbers. Used mostly as an integrated ram rocket. Where a fuel rich propellant burns and gives fuel vapors, okay, that mixes with the incoming air, which is decelerated to subsonic conditions, thereby increasing the pressure and the temperature, and combustion happens with the residue of the fuel rich propellant and the incoming air which has been decelerated and therefore pressurized and increased in temperature, expanded through the nozzle to generate thrust. So this is the basic principle of operation of a ramjet engine, okay, and the optimal operating point is in the range of 2 to 4, Mach number 2 to 4. What happens when you go to Mach numbers beyond 5 is that in the deceleration process or the result of the deceleration process is air at such high temperatures and pressures that there is very little room for addition of enthalpy by adding fuel, because temperatures are so high, whatever fuel is added, the fuel will simply decompose without adding enthalpy to the flow. So it does not make sense to go much beyond Mach, when the flight Mach numbers go beyond 5, it does not make sense to decelerate the incoming air to subsonic speeds, because the scope for adding enthalpy is very low. So combustion has to be conducted under supersonic conditions, and that is what is done in a scramjet engine. Here again this again is a 0 thrust at starting Mach number. Obviously this becomes effective only at Mach greater than 5, so it has to be taken to that Mach number through some other means, and the flow should not be accelerated to subsonic conditions. The flow remains supersonic in the combustion chamber. And fuel is added to this stream of this supersonic stream, which adds enthalpy to the stream, enthalpy to the incoming stream, leading to generation of thrust. Okay. In candidate vehicles where liquid fuel is used, again the droplet size controls the heat release. Here the heat release should not be too fast or should not be too low. The design is in some ways unlike any other propulsion system where the engine is designed separately from the vehicle. A scramjet is a special system where the vehicle design and the engine design must go together. Okay. So such air breathing systems are conceived as candidates for 2-stage to orbit and return. For cheaper access to space, to low earth orbit specifically, including exciting possibilities like space travel, where we could go experience space and come back using vehicles of this kind, and it is much cheaper compared to chemical propulsion systems, or rather rocket propulsion systems where both oxidizer and fuel have to be carried. Here only fuel needs to be carried. So that brings us to the end of this summary session, where I have very quickly tried to give you the key ideas involved, key fundamental ideas, and how those fundamental ideas are used in the design of propulsion systems of various kinds. Thank you very much.